So, hello everyone again. This is lecture 5 part 2 of alternating current. In the previous class we have started with a new discussion regarding the concepts of power in an AC circuit. Power factor, basically we understood the definition of power factor, which is basically the cos phi angle being generated in the formula for P is equal P, which is equal to V into I into cos phi, or basically I square Z into cos phi. Let us understand more about this using the examples. There are I think two to three examples which we need to understand, so that we can understand the basic crux of what this power factor holds. So, let us start discussion directly. So, this is lecture 5 part 2 of alternating current. I am Sameer Lavankar. Let us begin our discussion. Okay, so currently we are in the 7th topic here, which is about power factor, power in AC circuit, the power factor. After this is being done, we can move on to the final two application, which is LC oscillations and transformers. Okay. Okay, so power in AC circuit, the power factor. Okay, so these all things are already been explained. Let's move on directly into the example given here. Okay. So the example states that, please understand the example very carefully. A sinusoidal voltage of peak value 283 volts. Please remember, the peak value is given to you and not the VRMS value is given to you. Okay. So the peak value is given to you as this. So basically if I write this as VRMS, so VRMS is nothing but equal to this peak value by root 2. Okay. Fine. So, a sinusoidal voltage of peak value 283 volts and frequency 50 hertz, so value of nu is given to you in the question, is applied to a series LCR circuit in which capital R is given, capital L is given, capital C is also given to you in the question. First of all, the question asks is find the impedance of the circuit. Let us try to go one by one only. So, the first question is basically to find out the value of impedance. Okay. So, what is the value of impedance? Impedance is denoted by capital Z, which is nothing but equal to root over R square plus XC minus XL whole square, correct. So, just put in the value. So, what is R? R is nothing but 3 ohms, so it is 3 square plus what is XL? Please remember, XL is not omega C, it is 1 upon omega C. So, it is 1 upon omega C minus omega L whole square. Okay. So, here just substitute what is omega. Omega is nothing but 2 pi into nu. Nu value is given to you as 50, and second thing is, so capital C is given to you as 796 into 10 to the power minus 6 Faraday, and the value as capital L is given to you as 25.48 into 10 to the power minus 300. Okay. Just substitute each of these values. Finally, after calculation, just leaving the calculation for you, you will get the answer as nothing but equal to 5 ohms. Okay. So, this is the complete impedance of the circuit. Okay. Fine. The next question states that you need to calculate the phase difference between the voltages across the source and the current. Okay. So, it is nothing but you need to just calculate the value of phi. How is phi calculated? Phi is nothing but equal to tan inverse XC minus XL upon R, correct. So, it is nothing but equal to tan inverse 4 minus 8 upon 3, right. If you look at this very carefully, you do not even need to remember this, because it is nothing but a triangle is being formed with 3, 4 and 5 values. Okay. So, you remember these both angles, right. So, that is why this value is nothing but equal to minus 53.1 degree. Okay, because 4 minus 8, it comes out to be a negative value, and hence the value of phase difference between the voltage across the source and the current is basically minus 53.1 degrees. Fine. So, now since phi is negative, the current in the circuit lags the voltage across this source. Okay. Fine. Let us move on to the next question now. The next question states that what is the power dissipated in the circuit. Just currently we have just derived the formula for power. What is the value of power? Power is nothing but equal to I square R, right, or yes. So, this is the power dissipated in the circuit. So, power dissipated in the circuit is nothing but equal to I square R. So, how to calculate this value? Here, wait, here let me first write. So, it is here capital I has to be calculated first. So, this capital I is nothing but equal to I m by root 2, correct. So this is nothing but equal to 1 by root 2 times what is the value of Im being calculated. This value of Im is nothing but equal to the value of Vm. Please remember, Vm can be linked to Im, capital I can be linked to capital V. Okay. So it is nothing but equal to Vm by capital Z, right. So this is nothing but equal to Vm is 283 upon root 2 into 5, correct. So this is nothing but equal to if you just calculate its value, you will get the answer as 40 amperes. Okay. Therefore, what is p value? P value is nothing but equal to 40 squared into resistor R is nothing but 3. Okay. So finally, just mathematical calculation will give you the answer as 4800 watts. Okay. Now look at this very carefully. When I tried to explain you the value of power, I used directly the formula as P is equal to I square R. In general scenario, when we derived this, we used actually value as I square Z. Okay. If you remember correctly, when we were trying to understand the 4 cases of power factor, there was a line given there. The line generally stated that the power dissipated in an LCR circuit is always only and only due to the resistor, correct. So either you can directly use the formula P is equal to I square R, or you can even use the formula this P is equal to I square Z, but this Z is nothing but equal to R cos phi, correct. So if you just multiply, or basically it will be I square Z into cos phi, correct. So this Z cos phi, when you try to calculate, will come out to be equal to capital R only. Okay. So that's how this thing is same. Okay. So try to do at that as a homework. Just try to calculate the same value. As you know the value of Z also we calculated here, you know the value of phi also you calculated here, and therefore we can directly obtain the value as nothing but equal to 4800 watts. Okay. Fine. After this thing is being done, the final thing obtained required is nothing but power factor. So what is power factor? Power factor is nothing but equal to cos of phi, and cos of phi is nothing but equal to cos of this 53.1 degrees. So either 53.1 degrees or minus 53.1 degrees, in mathematical form of cos it does not matter. So it is nothing but equal to 0.6. Okay. So that's how this question is being done. Fine. Let's move on to the next question now. So listen to the question very carefully. So suppose the frequency of the source in the previous example can be varied. Okay. So we try to change the value of omega. What is the frequency of the source at which the resonance occurs? Okay. So first of all, the question asks is we need to calculate the value of frequency of the source at which the resonance occurs. If you go back to the concept of resonance, we actually calculated a formula so that we can calculate the value of resonant frequency. That frequency formula was simple. We denoted it as omega naught, which is nothing but equal to 1 upon root LC. You know the value of L, you know the value of C, just calculate it directly, you will get the answer as nothing but equal to 222.1 radians per second. Okay. So I hope this concept is clear till this point. The second question says that calculate the impedance, the current and the power dissipated at the resonant solution or resonant condition. So again same question, just go line by line, go very slowly as it is the first time. So under root of again nothing but R square plus XC minus XL whole square. Okay, it is nothing but equal to, everything is given to you in the question, just this time don't take the value as omega which is 50 hertz, take the value as omega dash which is nothing but equal to 222.1 hertz. Okay. So as you remember that at the value of impedance which is omega dash equal to 2.1 hertz, Xc will be equal to XL, and therefore what is the value of Z? The value of Z will be nothing but equal to R, correct. So even if you do not calculate, if you just use the simple theoretical concept which you have understood, you can directly obtain the value as 3 ohms. Okay. Fine. So we have calculated the impedance. The second thing is current. So current is nothing but equal to capital V by Z, right. So it is nothing but capital V is Vrms here. So I am just denoting everything by Vrms. So it will be 283 by root 2 to calculate the value of Vrms, and capital R is given to US 3. Therefore this time the current obtained is 66.7 amperes, right. If you remember correctly, what is the basic agenda or basic principle of resonance? The basic principle of resonance says that when the value of omega is equal to omega naught, the current produces maximum, If you remember, in the previous case scenario, we obtained the value of current as 40 amperes, but this time we are obtaining the current value as 66.7 amperes, which is higher. That means we are in the right sequence, correct. And finally, the last question says that we need to calculate the value of power. So, we know that the power is nothing but equal to I square into R, correct. So, what is I square R basically here? So, I square R is nothing but equal to 66.7 whole square into 3, that is nothing but equal to 13.35 kilowatts. Okay. So, if you see very clearly, here the power obtained was 4.8 kilowatts, right. So, this can also be written as equal to 4.8 kilowatts, but if you see for the resonance section, you are getting the answer as 13.35 kilowatts. Okay. Again, we can do this question as I square Z also. So, it is nothing but I square Z into cos phi. Please remember what is the value of Z obtained. Z value is nothing but equal to R, and what is the value of phi? Phi is tan inverse XC minus XL upon R. As XC is equal to XL, therefore the value is equal to 0. Therefore, cos 0 and cos 0 is 1. So, either you do by this formula or you do by this formula, every time the answer will be same only. Okay. So, I basically made you understood this concept also, as in you can use the formula I square R also directly. But please remember what is the value of I you are using, what is the value of R you are using, what is the value of Z you are using, what is the value of phi you are using. One more question can again appear, that what is the power factor here. Please remember the value of power factor is equal to 1. Okay. Please do not confuse again in this concept. The value of power factor is cos phi and not phi. Okay. Sometimes people generally make mistake here also. So, please remember power factor is designated or denoted by cos phi, which is equal to 1. Okay. Fine. So, I think that was the question. Okay. Let us move to the final question, one of the application part of this concept. Okay. Understand this example here. So, the example states that at an airport, a person is made to walk through the doorway of a metal detector for security reasons. If he or she is carrying anything made of metal, the metal detector emits a sound, correct. On what principle does the detector work? Okay. So, you may have heard everything, you may have even went through these metal detectors, correct. So, you just pass on through this metal detector, and if you have some metal across your body or anything in your pockets, a sound will appear, a sound will be generated, correct. Why does this happen, or what is the basic principle behind this concept? Okay. Understand this line by line. So, the metal detector works on the principle of resonance in AC circuits. When you walk through a metal detector, you are in fact walking through a coil of many turns. So, basically inside this there is a coil surrounding this door or door like structure. Okay. The coil is connected to a capacitor tuned so that circuit is in resonance. When you walk through with metal in your pocket, the impedance of the circuit changes. So, the value of Z will either increase or either decrease, okay, resulting in significant change in current in the circuit. And when there is a change in the current in the circuit is aligned in such a way that if there is a change, if there is a deflection in the current, there will be sound produced. Okay. So, this change in current is detected and the electronic circuitry causes a sound to be emitted as an alarm. So, that is how this complete concept, small concept of resonance is being even applied to FM radios also, so that we can get that particular broadcasting station to be emitting its sound or basically to emit its frequencies to us. And second application which we heard in this chapter only is in the usage of a metal detector. Okay. So, I guess that is the ending of this concept also about power factor. Please revise this concept very carefully. Please try to solve as many problems as you can regarding the power factor, and it will be good to go. Okay. So, that thing being said, I guess that is the complete ending of all the concepts we require for our understanding of now further concept, which are basically applications regarding alternating current. The first application is basically LC oscillations. This is also a concept only, but a sort of all the things which we have accumulated till now, all the data which we have accumulated till now, basically the understanding of waves, oscillations which we have studied in class 11th also will come into picture here. Okay. So, as the name suggests, LC oscillations. So, as you can see clearly, LC as in the circuit will be an LC circuit, and oscillations as in there would be some sort of oscillations of either current or voltage. We will understand what is it. It is not voltage as in or it is not as in current as in, we will understand what is actually happening, but some sort of oscillation will appear and the circuitry used is LC. Okay. So, let us try to understand this LC oscillations. I think only introduction would be done and then we can move on with the actual clarity in the next part of this chapter, next part of this lecture. Okay. So, LC oscillations. So, as I already explained, LC oscillations, as the name suggests, the only circuitry which this has is a capacitor and an inductor. Okay. So, we know that a capacitor and an inductor can store electrical and magnetic energy respectively, right. So, this concept was being explained in the EMF chapter, electromagnetic induction chapter. So, when a capacitor which is initially charged, please remember, very important, initially charged is connected to an inductor, the charge on the capacitor and the current in the circuit exhibit the phenomena of electrical oscillations, like oscillations in mechanical system, right. How is this oscillation being happening? What is this actually oscillation being explained here? I will try to explain. So, basically now till now what the crux says that there was a capacitor that was initially charged, but now there is, let us say, amount of charge which is flowing. The charge is flowing, we know what is the definition of current. The change in the amount of charges being flown from point A to point B per unit time is basically called as current. Hence, current is flowing and it is passing through what? It is passing through an inductor. Okay. So, when a capacitor which is initially charged is connected to an inductor, the charge on the capacitor and the current in the circuit exhibit the phenomena of electrical oscillations, like oscillations in mechanical systems. Let a capacitor be charged. Now, let us try to understand it mathematically what is actually happening, so that we can understand this oscillations concept more clearly. So, let a capacitor be charged Qm at t is equal to 0 and connected to an inductor as shown in this figure. Okay. The moment the circuit is completed, the charge on the capacitor starts decreasing, quite evident. So, basically there will be a flow of current and therefore, as there is a flow of current, that means there is flow of charges. Where are these charges stored? These were stored in capacitor. So, therefore, there will be a decrease in the charges in the capacitor. So, the moment the circuit is completed, the charge on the capacitor starts decreasing, giving rise to current in the circuit. Now, let Q and I be the charge and the current in the circuit at time t. Please remember, initially the Qm charge was there and at some time t the value of charge was Q and current is I. Okay. Since di by dt is positive, the induced EMF in L will have the polarity as shown, that is Vb is less than Va, and so according to Kirchhoff's loop rule. So, now I have to explain using writing, but understand this very carefully. A plus charge is explained here, so therefore a positive charge will be here and a negative polarity will be here as negative polarity is here. Okay. Fine. So, I think that was a small introduction regarding this concept. Now, I will start the discussion regarding the understanding of what are actually these oscillations being happening and how can we relate it with the actual damped, not damped oscillator, normal mechanical oscillations. Okay. So, I will continue this discussion from this concept in the next part of this lecture, and I think that will be the ending of this part also, and then we can move on to finally the next concept, that is our transformers. Okay. So, that thing being said, let me stop the discussion here only. Thank you so much.